All right, welcome to EE 220 Circuits 1. I'm going to go through the course and how everything works and what you're going to learn and what's expected and all that stuff. So I see that some people haven't read the, actually let's go this way. Here's my web page. You can click on and find out about all my research and what's going on there. You can see the course link there. That was on the previous link as well. So we'll click on courses. First thing, note that all of my previous lectures from past years are there. So if you think I'm getting old and I'm not doing as good a job, then you can go look at an older lecture and see how I explained it then. Okay, so, and there's also example quizzes, homework, all kinds of things there. So I'm not trying to limit you, and I'm not recycling things. So you'll see you have all that stuff right there at your fingertips. So here's our course web page 220. After each lecture, I will post the notes. The notes will be probably 6-ish or so before they're up. The videos will be probably within 15-20 minutes after the lecture ends. Unless there's a problem. So when you're taking the class, and you don't need to write everything down because you're going to have it at your fingertips to review if you need to. So if you miss something, you can go back and look at the video. Now, I don't use PowerPoint. I don't read to you. I will teach you, and when you don't understand, I expect you to ask me within reason, all right? And I will explain it, all right? I know the stuff. Yeah, I might not know something, but I know pretty much most of it, all right? And I can explain it, and I can adjust the course so that if you're not understanding something, we can spend time on that rather than pushing through a bunch of PowerPoint slides. Again, you have all these other semesters that have the course information and lectures and videos and homeworks and example quizzes that you can use so that you can do well. My goal is for everybody to get an A. All right, never happens, but I figure if everybody's getting an A, then I'm either really easy or you're learning. All right, if you're getting Fs, then I'm either a crappy teacher or nobody cares. All right, so I want you to get an A, and I mean that. All right, so here is the homework assignments. I make up the homework assignments and post them as we go along. You'll see that you have a homework assignment due on Wednesday. It's not a tough homework assignment. It's more to get you to follow the guidelines which are posted here, and I'll let you read through them at your own pace. Why that's not loading faster. One of the key things to note when you do your homework assignment, you only write on one sheet of the paper, and then you close the paper like this. So you write your solution here, and I'll go through that briefly. You close the paper like this. So it's like a book. This is on the left. And then your name, homework number, and date if you want, go here. And the reason that I do it like that is then when the grader grades your material, they will put your score here on the inside, and the scores are not visible when I'm handing back the homework, so that you will be able to see what your score is, but unless you show somebody, they won't be able to see it. And the reason that's important is when I do the grades, I'll get my Metallica placeholder here. I'll post the grades there. Let's go look at a previous semester. You will be able to identify yourself by your scores. You won't be able to identify yourself by your name or ID or anything like that. The reason I do it like this is people make mistakes. I make mistakes. The grader makes mistakes. If you're going through here and all of a sudden one of your scores was recorded wrong, you'll be able to see it. All right? Now, what happens when you and somebody or 3 other people have the exact same scores? You don't know which one's you, right? Who cares? It doesn't matter. You have the same grade. So if you say, well, I have the same, but I don't know which one of those is me. Who cares? All right? This way there's no information privacy issues or whatever, but that's why I have you do the homework like this. And you'll see, look in here, there's only a couple empty seats. You'll see that organization in a class this size is really important, and you have to follow what I'm saying, or else the grader will be spending 40 hours a week just grading, and I can't have that, okay? So let's go back to the homework guidelines here. And let's see, right here, then right here. And you can read through these on your own. I'm going to be, homework's due at the beginning. If you come in late, and I'll talk more about this in a moment, don't run up here, oh, homework's due. You can turn it in afterwards, all right? I don't want you to freak out on me, all right? If you're going to come in late, we'll have some other discussion about that. Regularly, we'll have some other discussion about that. Go through, look here, then there's a nice little example, the fold, there's the name, there's the solution. When you do your solutions, you put the problem statement, then you put your solution, and you integrate it with the simulation so that everything's really nice. So when you go to study for the midterm, everything is nice and organized in your homework. It also makes it practical for the grader to get through the homework in a reasonable time, all right? So you go through and look at all of these, answers boxed, and then it gives you some hints. You can look at this on your own. If you don't have, if you don't follow the guidelines, I'm going to tell the grader the first time to give you a warning. The second time I'm going to say start taking off points, because you can't grade this many students with as much homework as I give and quizzes and not have significant time unless everything's organized. So you have a homework due on Wednesday, Monday is Labor Day, and then another homework due on Wednesday, probably next week, and I'll post the next two homework so that they're available for you to look at. All right, your current grades will be right here. You'll be able to see who you are. I put some Metallica lyrics here just so it wasn't a broken link. I can't tell you how many times I've had people say, I didn't know you were a poet. I'm like, I am not. So anyway, this course will make extensive use of LT Spice. This is a simulator. There's also links here for tutorials and other things. Frankly, you're going to be able to pick it up with just what I do. If you're a Mac user, there's a YouTube video on using the Mac, all right? So I will do some LT Spice today for the homework, and we'll show you how to use it. So I don't know how much of this you'll need to use, but if you do, it's there, okay? This SPICE, the simulation program with integrated circuit emphasis, is a simulator so that when you look at circuits and you solve for what's going on, you can then put the circuit in the simulator and see what's happening. Okay, so we'll do that today. The 220D discussions for the past semesters, I did these videos. I taught 220D a while back. So these have more examples of simulations. I mean, holy cow, there's so much here to help you. You just have to look at it. Let's see. These are your times for the discussions. The textbook is here. You probably all have downloaded it. I know you're probably disappointed you didn't have to spend money on the book. There it is. I don't know how much I'll use it because last semester when I taught circuits too, I did give problems from the book and the students hated them. So I probably make my own homework problems up because the students seem to get more out of it that way. I'm pretty sure that's the case. Here's our grader. I don't grade the homework. I don't grade the quizzes. I grade the exams and that's it. I'll ask him to have office hours for help, but generally the discussion session's all you need. All right, let's see. Final exam, Monday's Labor Day, then Monday, November 11th, Veterans Day. Here's the course content. Here's the grading. I don't generally like this taking off points, you know, like Hogwarts or whatever, -2. But when we don't follow the homework or the policies, because I need to make sure I can see what's going on and everybody's following, all right? So let's go through here and hopefully I won't take any points off anybody, but we'll see how that goes. So no electronics, including laptops, should be used. So if you have a laptop open, that better be put away, all right? If you need to use your calculator, that's fine. I want you to pay attention. You'll get something out of this class. What's the most important part of building a house? Foundation. Same thing with your education in electrical and computer engineering. You're going to get a good foundation in my class. I'm not going to waste your time. All right? Don't play with your phone. I don't want to share your attention with your phone, all right? Now, having said that, if you have an emergency and you need to look at your phone, tell me, talk to me, let me know, all right? Because I don't want to say, hey, you're looking at your phone and you have a family emergency that you need to be aware of, all right? Just talk to me and let me know what's going on. What I don't want you doing is looking at the internet or, hey, what's going on here, instead of paying attention. Don't put your backpacks up or try to hide your phones behind. I've got stories, and you wouldn't believe the stories of students. I'm going to watch TV during his lecture and stuff like that. I don't like that, so don't do that. Let's see. I had one student that wasn't passing the class, and like towards the end, he puts his backpack up there, then he puts his phone there and he plugs in his earplugs and he's like really down, like, what's going on over there? So I walk over, he's watching TV during my damn lecture. So why wouldn't he just leave if he didn't want to watch the lecture? That's a good question. Quizzes. You find if you leave, you don't get the quizzes and then your grade goes down even more. And I will give quizzes most of the time at the end, but sometimes in the middle and sometimes at the beginning, depending on what kind of behavior I need to correct. All right. Well, I'm a big fan of starting and stopping on time. Some faculty don't start and stop on time, and that forces the students to come to class late. All right, well, if that happens and then the students start getting quizzes at the beginning where coming in late's bad, then they're going to go back and tell the professor, hey, you need to let me out on the right time. I won't let you out late unless I just have total brain fart, okay? And I'll start on time unless I'm going to learn everybody's name when I hand back the homeworks. That takes some time, but I'll do my best to start on time. If I'm not here early, then I'm late. That's a good lesson, all right? Don't show up late. That's not good, and you shouldn't tolerate it. For your professors, if they show up late, you should not tolerate that. All right, I won't accept late work. I mean, if you come in late and you need to turn it in at the end of lecture, okay, but I can't keep track of late work if you say, oh, I need to go wherever, see the new opening of such and such movie, and can I turn in my homework the next lecture? It doesn't work because there's too many students and it's hard to keep track of the homework. So let's say, because I have trips and I do things, that you can't make it to class. What are you going to do? I don't want to keep track of early homework. Give it to somebody you know to turn in, or take a picture and email it to the grader before it's due. I couldn't make it to class. Copy me on it. I know I say don't email me. Copy me on it so I know what's going on, and turn it in that way. Stuff happens. I can tell you, I've been teaching almost 30 years, and I can tell you things that would blow your mind in interacting with people. Don't think that it's like, oh, he wants this. I know stuff happens. When things happen, take care of it, all right? Send it in early. Don't come in after the fact. Well, I could have emailed it in and taken a picture, but I didn't. I don't tolerate cheating, so don't put yourself in that position. Email questions to the group, then hopefully some other student in here will get to answer the question, and it won't just be me. If you have questions for me about the course content, come and see me during my office hours. Talk to me. I don't like this impersonal email. I want to talk to you and interact with you. I don't want to answer and try to answer emails. The other thing is, if you have a question because I didn't do something well or cover it, like what is Supernode or whatever, there's chances are everybody else in the class has that same question. When you send it to the group, then we can answer it, or I can answer it, or someone else in the class can answer it, and it's all there for everybody to see. Don't send email to me via the group. Hi, Dr. Baker, I know you said not to, but I'm sending it via the group. I mean, that defeats the whole point, all right? Let's see. Any questions? Should be a good semester. We ready to get going? All right. So everybody knows the homework's due. You'll put it in on Wednesday right up here. We're going to start up with some basic stuff, and I'm going to do some simulations. Now, When I do simulations, what I'm going to do is I'm going to put them in this folder right here that I'm going to create on my desktop. And you know what? Let's make sure we're running. And we are. So let's extract here. And I'm going to save it in here. So every single simulation that I do, you're going to have a copy of, because after class, I'm going to upload that to the course webpage, and then you can download it and use it. Okay? So you don't need to take notes unless you want to. You can sit back and relax and think about what I'm saying, and you can look at the simulations on your own time as well. Any questions? So don't come in the middle of the semester and go, I didn't know that you had the simulations on the course webpage. You think that hasn't happened 100 times? Yeah, it has. All right. So let's go talk about voltage sources. And there's a few things right now I want to burn. Does anybody have any questions or comments? All right. There's a few things I want to burn into your heads just to begin with, because we're going to see them over and over in this class. One is voltage source or battery. We'll just stick with battery to begin with. Now, battery, if you've ever used a battery, has a plus and minus terminal. This is a battery, and it has some voltage, let's say 1.5 volts. All right? That means the potential or the voltage difference between here and here is 1.5. I'll go over that more in a second. Okay, so what I'm going to do is I'm going to add this little symbol right here that's called ground. And we'll talk more about this through the semester. But for now, ground is our reference. So whenever you see ground, that's 0 volts. All right? This voltage then is uphill. It goes from minus to plus. It goes uphill. So this is 1.5 volts. So I want you to burn into your heads. Whenever you see that, it's a 1.5 volt source. So if I go back over and I say the following, or actually, why don't we pause and put this in Spice? That'll be something simple that we can do. This is my reference. Whenever I see this, I get 1.5 volts. I don't think deep. So let me ask you this. What if I have this? And I say, what's the voltage right there? 1.5. All I did was flip it around, right? Easy. All right, so let's go start LT Spice right here, and then say File, New Schematic, and then I'm going to do File, Save As. Let's go put it on the desktop right here, and I'm going to call this, how about Lecture 1, Example 1. Then I'm going to come up here to this little gate here, this little AND gate that's component, and I'm going to grab a voltage source. Now, first thing I notice, I can move this around. Notice the lower left corner there, Control R, Control E. That flips this around. So if I press Control R, it just rotates it. If I press Control E, it flips it, mirrors it. Okay, that's really useful as you start drawing more and more schematics. So I'm going to plop this down, and I'm going to hit Escape to get out of it. And I'm going to right-click here, and I'm going to put a value of 1.5 volts. Okay? Then I'm going to go up here and get a ground. I'm going to plop it down, and then I'm going to go get the wire, and I'm going to draw a wire. All right, and I'll hit Escape. That's my little voltage source, and now I'm going to poke the running man, which means I'm going to run the simulation. And it doesn't know what I'm running, but I'll run it, and it says, what do you want to do? You want to do a transient, AC, DC? You'll know all of these by the time the semester is over. I'm just going to do a DC operating point. What's the voltages in the circuit? Click OK. It plops down the .op there, and it says node VN001 is 1.5 volts. That's what it's calling this wire here. Notice if I put the wire, or I put the cursor on the wire, I see 1.5 down there. Okay, so let's pause and talk homework. Any questions on this first? So far easy, right? Because you're going to have homework that's going to make you do this. You want to show that your homework matches, your hand calculations match your simulations. So let's poke this again. And then I'm going to go over here, and I could make this smaller or whatever, but what I'm going to do is I'm going to grab the snipping tool, and I'm going to do this, and I'm going to come over here, and this is my verification, and actually I'm going to change it to red, and then I can put a circle around here, and I can say that node is 1.5 volts, and that's what I paste into my homework to show the simulation matched. Key takeaway, I'm drawing on here to make it easier for the grader. I can take my pencil after I've got my homework and I can draw on that and make it easier for the grader as well. Because one day you may be the grader, and if you have 65 students to grade twice a week, quizzes and homework, you'll understand how important it is to make things clear for them. Okay, any questions? Okay, so now, I close this, and I hit save just to make sure. I go back and I look in my little folder, and there's my little simulation now that I can double click on it and run the simulation directly. And you'll have this after class, right? Okay, so now let's go back and do a couple more things here. Any questions? Okay, all I'm going to do now, and this is something I had a problem with when I was learning, so I'm going to flip the battery around. Okay? And I'm going to say, okay, here, before I add it, the minus connected to ground. Now I'm going to do this. And I'm going to connect the plus to ground. So when I was learning, I'm like, wait, what? You can't ground the positive of the battery? That doesn't work. Well, yes, you can. In fact, a lot of diesel cars, they ground the positive and they use a negative battery. Okay? So I ask now, what is this voltage right here? Minus 1.5. And similarly, if I do the following, and I ask what's this voltage, it's minus 1.5. Okay, so, trivial question. What's this voltage? 0. This voltage you just told me is minus 1.5. So voltage drop across something, if I'm looking at this, would be this voltage. We'll call this voltage A minus voltage B. So voltage A minus voltage B equals, let's see, VA is minus 1.5. VB is what? 0. Says that the potential from here to here is minus 1.5. Everybody follow that? When I say voltage at a point, it's always with reference to the ground. What's the voltage right here? It's with reference to the ground. What's the voltage right here? With reference to the ground. If I ask you what's the voltage across something, ground may not be in there. It would be like if I take and I've got a circuit like this, and I ask, what is the voltage like this? This is 1.5. What's this voltage? The voltage from here to here is 1.5. I may have a voltage here of 100 volts, and the voltage here may be 98.5 volts, but the voltage between here and here is 1.5. I don't know what the absolute value is. Does everybody follow that? Oh, and one thing I failed to talk about is the grading, and that seems to be, because I don't care about grading, I care about learning. But that is something that students care about. We will have homework basically every day. I figure it's not that hard. It's just keep you working on it so that you have a good foundation. We will basically have quizzes almost every day too. So what will you have on Wednesday? Quiz on what we're covering right now. And it's not meant to challenge you, or it's meant to just ensure you understand what I'm talking about. All right? And where, if you want to see example quizzes from past semesters, where do you look? The website. It's got all kinds of example quizzes. You know what to study. So everybody should get an A, right? It never works like that. All right. Let's do a couple more things, and then we're going to talk about Ohm's law. Or actually, let's go ahead. Yeah, one more thing. Actually, let me do it on here. When I draw a circuit like this, and we'll cover this more in a moment, and I put a ground, and I say, okay, when I have a circuit and I supply like my phone or whatever, and I'm coming around here and I've got my battery, electrons get attracted on one side, go through the circuit, and go back to the positive. So the electrons move like this. Does everybody see that? They leave the minus, they go around. However, we draw a current like this. It flows this direction. Okay? Now I want to bring up something here, and we'll talk more about this in the semester. But you see the current that leaves here, opposite of electron flow, is the current that comes in this side of the battery. Does everybody see that? So if I ask you how much current flows down on the ground, how much current flows down from the battery to the ground connection? None. The ground is a reference. And in fact, in your house or apartment, what do you call the circuit that's job in life is to ensure there's no current on the ground? When you plug your hair dryer in, if you have hair, unlike me, and you need to blind that, what do you call that circuit? It's got test, reset, GFI, ground fault interrupter, ground fault circuit interrupter. And that circuit is to see if there's current flowing on ground, or it makes the hot and the neutral see if the currents are equal. Because if not, you could be the path of the current and get shocked. So you don't want current on ground. Current on ground's bad. So here, I draw the ground, but no current's flowing on it. So everybody got that? Okay. So now, let's go talk about Ohm's law. So Ohm's law looks like this. And we're going to go through this backwards and forwards because this you'll use over and over and over. So I've got a resistor here. I've got a voltage, and now I have a current that's flowing. And the way I think of this is I think of it like water. This is like a pump, and that's pumping water through the load. If I make the diameter of the pipe small, what happens to the resistance? Goes up. If I make the diameter of the pipe wider, what happens to the resistance? Goes down. So this is exactly what I have in this circuit. I have a battery driving a resistor. What in your general use of life, what is a resistor? Give me an example where you're walking through your house and you see a resistor, maybe. Well, the old incandescent light bulbs. Before long, people will be like, what are those? But another one is the heating coil on your stove. That's a resistor that you're putting voltage across, and it heats up, and you put a current through it, and that generates power to heat your, whatever you're cooking, all right? So if I look at this and I ask, what is the voltage, and I'm going to go through this several ways. What is the voltage here equal to? What's the voltage across the resistor? What is the pressure across this resistor? Well, let me give you a simpler. What is the pressure from here to here that we just went over? I asked trivial questions, so if you think the answer is easy, you're probably right. This voltage is V. And in the examples I gave, if V was 1.5, that would be 1.5. And just because that kind of scared me a bit, what are these right here? Wires. Okay? So if I ask, here's a wire, what's that potential or what's that voltage versus that voltage? Same. So if I ask, what's the voltage across this resistor, what is it? V. I'm applying that voltage directly across the resistor. Everybody see that? If I ask you, what's the voltage right there? When I ask what's the voltage right there, it's with reference to ground. What is that voltage? 0. And what is the voltage right there? V. And what is the voltage across the resistor where one side's a ground? V. And so Ohm's law says that voltage equals current times resistance. So if I increase the resistance, my current goes down. If I increase or I reduce the diameter of the pipe, the amount of water flowing goes down. Everybody follow that? Okay, so let's do an example. Let's say I have this. Oops, I'm getting lazy. Don't make me lazy here. So I drew two grounds, and when you do that, it's assumed they're tied together. And I'm not going to be lazy yet. I'll be lazy soon enough. Okay, if I ask now, what's the voltage across here like this? 1.5. Let's say I try to be tricky because I'm giving my quiz, and I say, what's the voltage across the resistor like this? Okay, think about it. What have I done? It's this voltage minus this voltage gives me 1.5, but what if I do this minus this? Minus 1.5. This is the same voltage, right? I just defined it differently. This would be 1.5 minus 0. This would be minus 0 minus minus 1.5, which is positive 1.5. I've just flipped the polarity. And if you got that, good, because I don't think most of you did, but we're going to go over it again. All right, so let's do this simulation. Any questions? Oh, I got a question. How much current flows in the circuit? Well, using Ohm's law, I equals 1.5 over 1K, which is 0.0015 or 1.5 milliamps. Oops, what happened? All right. Any questions? We're going to simulate all of this. Okay, so let's go back. And because I'm lazy, let's double click on this and do File, Save As, and we'll call it Example 2. And then I'm going to get this little hand out, which is the stretchy hand, and I'm going to move it up like this. And I'm going to move this down a little bit as well. Then I'm going to grab resistor here, and that resistor is 1.5K. And I say that as if everybody knows what's K mean? 1,000, so 1,500 ohms. Okay? If I don't tell you something and I say something and I assume you know it, you don't know it, tell me, all right? And now I'm going to do this two ways. I'm going to come over here. I want you to learn the tools. Now I'm going to come here, go down, come here, go down. Then I'm going to right click on this node. And I'm going to say highlight net. And look what just happened. It says those two are shorted together. But I'm not going to do that to begin with. But when we get going, I'm going to be lazy and draw the schematics like this because it makes it have fewer wires. So I'll get out the scissors. I'll go back here and I'll go like this. And then I'll get out the scissors and cut this, or I could stretch it back. And I'll get this little hand here, move it up. Of course, the big hand detaches it and lets it move around. Okay? And then I'm going to be fancy, and I'm going to call this wire something. I'm going to call it, how about VA? And that's just the name I'm giving it so that it's easier when I do my homework and I compare. Any questions about this circuit? Yes? Ah, right here. Label net. And then I'm going to come up here. And most of the time when I make the homework, I always do this before I take the snip so it's smaller. And I hit run. And it says, hey, VA is 1.5 and the current is 1 milliamp. Now, a couple of things that will drive you crazy if you don't understand. You see it says IR1's 1 milliamp, and that's exactly what we calculated, right? So no problem showing that that's correct. Now, you see how it says IV of 1 equals minus 1 milliamp? SPICE defines positive current flow is from plus to minus. So it defines it. Let's take a snip and I'll show you. It defines positive current flow as going like this. But which way is our current flowing? Our current, the way we've defined it, and we define it because we're the engineers, we defined it flowing around like that. Does everybody see that? Now, any questions? All it's saying is, hey, I'm defining current as positive because it doesn't know, plus to minus, and I'm doing it opposite. Okay, one other thing. A resistor doesn't, so any questions on that? I don't want, you'll use that for, I mean, if you take my IC design class and we do like a switching power supply and you're looking at the current and the efficiency and you get a negative current from a battery, you'll use that over and over again. Don't get confused. That's just the way it's defined, okay? Any questions? Okay, the other thing is the resistor, doesn't matter which way you put it in, right? So when you put it in, SPICE just assumes one direction is the resistor, is the current flow. So watch what happens when I do the following. You need to know this for your homework. You get the handout, and then you do a Control R and Control E. You flip it around. Same exact circuit, looks exactly the same. You hit Save, and now you hit Run, and it says, hey, now my current's negative, but I calculated it as positive. What the hell's going on here? Just flip the resistor around. It doesn't know which way you're putting it in and which way you've defined the current. Does everybody follow that? I don't want you to get frustrated on these homework assignments. I want them to be stress-free, learning how to do the proper format kind of thing. Any questions on this? Yes?
What did you mean by defining the current?
It has to pick a direction. So like, here, that's a good question. So let's go back to our circuit here. You see how I defined the current flowing like this? Why? Why do I need to define the current flowing like that? Because there's a battery and it goes from plus to minus? I don't need to do that. I can flip it around and have it the other way. So let's do an analysis of the same exact circuit, noting that when I picked the current going this way, I got, did I use 1.5 and 1? Why did I get 1 in that? I just realized. I used 1.5K instead of 1K. That's why I got 1. Oh well. So when I make that mistake in the future, correct me. I don't mind being wrong, okay? Sometimes you learn more from being wrong than being right. So I picked the current going this way. It's the same exact circuit. What if I pick it going this way? I'm deciding which way the current flows. Unless the problem tells you. What do you think the answer is going to be when the current goes like this? Negative 1.5. Everybody see that? All right, so let's do that problem. So we got same exact circuit, 1.5, 1K, and then now I'm going to pick the current going in this direction, or this direction, or this direction, or this direction. Does everybody follow? So since I'm learning, I'm going to go back and write Ohm's law. I'm going to write it like this. Plus minus current flowing down, V equals I times R. Everybody agree with that? But what if I do the following? Plus minus V equals I. What do I do different here? How do I change it so that they're the same? Everybody see that? So when it goes plus to minus, it's positive. When it goes minus to plus, I just negate the current. Anybody not follow that? So if I go back over here, the voltage is 1.5 because I'm physically placing the battery across that 1K. That's equal to minus I times 1K, or I equals minus 1.5 milliamps. Simple circuits, but if you follow these down the road and you're able to, oh, the current's going from minus to plus instead of plus to minus, that just means I use minus I, everything becomes easy. If in 6 weeks we're doing this and you go, why did you use a minus sign there for the I? It's going to be painful. So learn it now, all right? Any questions about this? So let's go back now and look at the simulation. Let's close this. Let me fix this one at least. Put it back at 1K. And now I run, and I don't know which way the battery or the resistor is. I have to look and see what the current does. Oops. And I see the current through here, if I look, is, let's see if I can get it. You see in the lower left corner? So it says minus 1.5 milliamps. Well, I have to know. I have to turn it around if it's in the wrong way. And I don't feel bad and I don't think like I'm cheating if I do that because I don't know which way Spice put it in. Everybody follow. Okay. So let's save this one. Any questions? Let me do one more example. And then I want to cover the circuit. I always tell the students at the beginning of the semester, this circuit's called a voltage divider, and you're going to use it over and over and over. And then about halfway through the semester, you go, you weren't lying. You use it for everything, all right? Just repeatedly. Okay, so let's do some more circuits. I would pick one from your homework, but they're not the most challenging of problems. They're there to make you make sure you understand everything. So let's do this one right here. And let's put the reference up there. Let's go here. Let's put the resistor right here. And let's call this 2K. And then I want you to find the current that's flowing. And let's define the current that's flowing just some crazy way. Let's define it like this. Then I want you to find this voltage, VB, this voltage, VA, and then the voltage across the resistor. Let's call it V2K. And if you're following, you can see there's a lot of trivialness here, but I want to make sure that everybody follows. So does everybody see I'm trying to do something crazy with the little circuits that I have? All right. So what's the easiest question to answer? VA, okay, VA is pretty easy, but I was thinking even easier than that. VB, what is VB? 0. You don't think deep. What is VA? Minus 1.5. Now let me pause for a minute. Here I am. I'm sitting up here, and I got a few hair on my head there, and then I'm going to run downhill, and I'm going to run over here. Am I going uphill or downhill when I go from plus to minus? Downhill. So I know this voltage is 0, so if I'm going downhill, won't that be at a lower voltage than 0? So that's how I know that it's minus 1.5. Does everybody follow that? Now, if I ask, what is this voltage minus this voltage? It's 0 minus 1.5, or 1.5 volts. So the potential difference between here and here is 1.5. Now, I did it with math, but when you see a battery like that, and somebody says, what's the voltage difference between here and here, and it's across the battery, you don't need to think deep. It's 1.5. Everybody got that? Okay, so now, what is V2K in terms of VA and VB the way I've drawn it? Well, in terms of VA and VB, then we'll go to the number. It's VA minus VB. Anybody not follow that? You could argue these are pretty trivial, but if you understand this, it makes things easier as we move forward. Anybody disagree with that? Anybody agree with that? Okay, so I could write that as simply VA, because VB is 0, which is minus 1.5 volts. This is what I would ask you on the quiz. I'd give you this circuit. I'd say, what is VA? What is VB? What is the voltage across the 2K resistor in that direction? And what's the current flowing in the circuit? Let's do the last one. Any questions? Okay, so I'm learning. So the first thing I do is I draw my little plus, minus V, and I, and that's I times R. Or I do this, and I do plus, minus V, and I, and that's V equals minus I times R. And as everybody see, I could flip these around. It would just be taking this circuit and turning it upside down, or taking that one and turning it upside down. Memorize those. Don't be afraid on the quiz or when you're doing them to write those out so you can cheat and look at them and see what's going on. Okay? So now, What do I use right here? I get plus minus, so I'm using this one, and so I say I equals V2K over R, which is minus 1.5 volts over 2K, which is 750 microamps, minus 750, which is 3/4 of a milliamp. Any questions? I'm going to sim it. Does it make sense? You see how we're looking at all these different combinations of batteries and resistors, right? No questions on this, right? All right. So let's go sim it. And this is the way I defined my current. I know what the answer is, minus 3/4 milliamp. I go back over here, and I'm going to start from scratch again. I'm going to do File, New Schematic, File, Save As, and then I'm going to call this Lecture 1, Example 3. I'm going to go grab the battery, and that went like that. I'm going to grab a ground just by pressing G. Whoops. And then I'm going to grab a resistor. How do I get it sideways? Control R. And let's zoom out a little bit with the little minus sign there. I don't know which way SPICE is picked as positive current flow through the battery, and I don't care. I'll just flip it around if it's wrong. And then I go here. And then I go over here. And then I made this resistor 2K. And then I made this battery 1.5. And then because I want to get used to doing quality organized work, I'm going to come up here and call this VA. Plop that down here. And then I'm going to right click and call that VA. But I know that I'll have problems if I do that. So I'm going to right click here and call this VB. Any questions? Yes? Yeah. Just right click on the resistor, right click on the voltage source. So Control R rotates, Control E mirrors it, right click changes the value. The big hand moves things, detached from the wires. The middle hand stretches things. So it keeps the component attached to the wire and stretches stuff. Okay, I'm going to do it a little bit different this time. I'm going to go up here to, when I poke the running man to run the sim, I'm going to do a transient simulation, which means time is on the x-axis. So I use dot operating, will tell me what's going on, which you probably should use most of the time, but here I just want to show you a different simulation. Transient for 1 second. And then I'm going to make this, fill the window. And what I'm going to do is click here, and I'm going to come down here, and I'm going to click on VA. And you see VA is minus 1.5 volts. Does everybody see that? Then I'm going to go click, and it's going to show me which direction my current is. Is that the way I define my current in my circuit? No. If you look, I define it the other way, right? So I'm going to go grab the big hand, and I'm going to grab that resistor, and I'm going to flip it around, rerun the sim, and now when I plot the current, it's going to be my 3/4 of a milliamp, which I see on this right side. But you know what? I don't like that. So I'm going to right click here, and I'm going to go add plot plane. Then I'm going to drag this one up, and then I'm going to take the little arrow here, and I'm going to stretch it over. And then I could adjust the scale to show it better. I could adjust the scale here to show it better. But I can also go with this window selected, and I can get a bitmap to the clipboard instead of using the snipping tool. You see how easy it is? And then I can snip it, or I could snip it and draw an arrow down with the current going through to show that my hand calculations matched the SPICE simulation. Any questions about this? I got a question. How do I show? Now, so before I do that, notice in this directory here. I got a bunch of stuff. When I have my my control panel set up to delete these files, the raw files, after I close the simulator. But what if I want to rerun the sim and I don't want to have to click all this stuff again? I want it to just pop up. What I'm going to do is I'm going to click this window and I'm going to hit save. When I hit save, it generates this little file here called a PLT file or plot file. So now watch what happens. I'm going to close this. So I want it saved. Now I'm going to reopen it. See the plot file? And now I'm going to hit run. And voila, everything plots back to what I had. And that's really useful if you're in like senior design and you've got 50 traces because you're doing some complicated schematic, all right? You don't have to go through every time and select everything. So now I'm going to right click on this, get rid of the current for now. Then I'm going to ask, how do I plot the voltage across the 2K? Because this is a simple circuit, but what if I have a really complicated one and it asks you the voltage across this component in the middle of the circuit? So what you do, here it's kind of trivial, but what you'll do is you'll right click on this and you'll say minus V of VB, or V just to make it the same. It does the cases and sensitives for SPICE. And you hit enter, and it's not liking that I labeled this node. But if that's the way you would do it if it was, if this was another voltage, is you just right click on this expression and then say minus, and then get the other voltage that you've labeled. Does everybody follow that? And that would show up at the top, and then you could say, hey, I did it right. Any questions? All right, next thing. Is anybody disappointed that you're getting information on your first day of class? All right, we don't have that much time, and we got a lot to cover, and I want to make sure you get something out of the class. Okay, so the next thing I want to discuss is a voltage divider. And then I'll do a couple examples of that, then we're going to talk about current sources. Okay? So voltage divider, let's make the circuit a little more challenging. And this is the one I say people use over and over again. Let's call this voltage V source. And then let's have two resistors, which I'll call one R1 and the other one R2. Oops, I'm getting lazy again. All right. First question. Let's sketch the current. Let's draw the current in the circuit. So I'm going to draw the current flowing like this. And I'm going to call it I. And then I've got two resistors now impeding or resisting the current. How do I calculate those? R1 plus R2, right? V over R1 plus R2. Resistors in series add. So I ask, what's the voltage between here and here? Yes. Okay, when you see a voltage source like that and someone says, what's the voltage across the voltage source? Don't put brain power into that. The answer is Vs. If I ask you, what's this voltage right here, that's with reference to ground, what's the answer? Vs. Okay, don't waste your mental energy on those. Those should be bam, like that, all right? So I get Vs from here to here. What is that voltage dropped across with that current? It's dropped across, the Vs is dropped across R1 plus R2. Everybody agree with that? Okay, now, this voltage right here I'm going to call VR1. What is VR1 in terms of R1 and I? What's that? No. Wait. Think for a sec. This is the way you need to imagine this. This is a pump. That pump is pumping water through the resistors. And so the water flows through the resistors and back to the pump, back in the drain, back in the lake where they're pulling the water out. The same current flow in R1 as in R2. You're going to say, no, tell me where the water comes from that's different from R1 and R2. It's a pipe that's going through both. Does everybody follow that? Okay? So now if I ask, you say, wait, I'm learning. Put up the thing at the crutch. And I go, okay, plus minus I, V equal I times R. And then my crutch here will, how about let's do this, just to be different. I just have been sketching it the other way. I just flipped it upside down. So which one do I use for this? I've defined VR1 as going plus to minus, so which one am I using? This one. So I ask now one more time in terms of I and R1, what's VR1? I times R1. Anybody not follow that? Anybody follow that? All right. So now let's do VR2, the voltage across R2. What's VR2? You would agree that I is just flowing down. That's equal to I times R2. Everybody would agree with that, right? Okay, so now we're going to get our voltage divider equation that we're going to memorize and use over and over and over and over and over. Okay? The voltage R2 is putting this current in here is Vs times R2 over R1 plus R2. Anybody agree with that? That's the equation we're going to use over and over again. So when we see this circuit, we don't have to solve for the currents and all that. We just know the voltage across R2 is the divider, is the source times R2 over R1. This is even used in op-amp circuits, which we'll talk about later in the semester. Any questions? Yes?
Okay, so that equation always confused me. So what usually goes on top?
If it's the voltage across R2, then R2 goes on top. If it's the voltage across R1, then R1 goes, just substituting this in here.
So there's no loss after R1.
What do you mean loss?
Like, no, so resistor controls the flow. So it's not like a reduced flow.
No, the water flowing in the circuit. What's circuit mean anyway? Let's answer that. That's a good one. What does circuital mean? Returns to the point of origin. All right, that's why circuit's always circuital. Return to the point of origin. The water that flows in this resistor and this resistor is the same. There's no other water in the circuit, no other current in the circuit. Everybody follow that? It's got to be. Okay? So, if I look at this, I want to find the voltage across R1. My brain shuts off. Oh, it's Vs times R1 over R1 plus R2. I want to find the voltage across R2. It's Vs times R2 over R1 plus R2. I'm going to use this over and over again. The key point where I can use this, the same current flows in both circuits, or in both resistors. Any questions before I do an example? This is the voltage divider. Okay? You can also call this an attenuator because it attenuates or drops the voltage down from your source. Shall I proceed? Yes? Ah, that's a good question. Let's see. I'll just write the answer. How's that? Because if you have a third resistor, then this current becomes R1 plus R2 plus R3 into Vs. And so if I have a circuit like this, R1, R2, just put them all like this. R3. Then if I call this voltage VR3, then VR3 equals Vs times R3 over R1 plus R2 plus R3. And VR1 equals Vs times R1 over R1 plus R2 plus R3. Now I'm going to do a tricky one. What if I do this? Oops, sorry. Everybody follow that? But the key thing here is I don't spend, oh, what's that circuit? Let me waste 15 minutes while I'm taking the professional engineer's license. That you can do in seconds, right? I say that and then I think to myself, how many people even know professional engineer PE, that's the license when you want to work and do public work and all that. So they know that you're competent and aren't going to kill somebody or something like that. All right, are we ready for an example? Okay. Oh. I had a student a few years ago, I didn't even know you could do this, but he was a senior and he was so confident with his circuit abilities that he took the professional engineering license and the fundamental engineering test, the PE test and the FE test in one sitting. And he passed both of them right out of school. So then all he had to do was work 4 years underneath the PE in order to get his license. Because you need a total 8 years, 4 years is your degree, and then 4 years of experience. And so he was all set. And he said, I might as well do it now while it's fresh in my head. I'm like, I didn't even know you could do that. Okay, let's do this example right here. Let me do an easy one to begin with. So without doing any math, I want you to just look at this and tell me what the voltage drop across each 1K resistor is and why. 1 volt. Why? Same current's flowing in that circuit, right? You have to have the same voltage across the resistors because they have the same value. So you get 1 volt across each 1K. Let's prove it with math. Does that make sense? I don't want you to just have, oh, what'd you learn today? Math. I want you to be able to look at something and know what's going on and kind of feel it. Okay? So if I look at that and I want to do, let's just pick this voltage right here. That's equal to 3 volts times 1K over 1K plus 1K plus 1K, which is 3K over 3K, which is 1 volt. But you didn't need to do math. You could look at this before. You don't see a circuit and immediately your brain goes to math, all right? I want you to look at a circuit and try to think about what's happening rather than, oh, how do I write equations about this, okay? And if I ask, what's the current flowing in the circuit? That 3 volts is driving what? 3K. Okay, so here's your pressure from your AC. It goes through a duct and it drops the pressure down a little bit. Goes through a vent, drops the pressure down a little bit more. Goes back to the return. Where's the return? That's the duct. Where's our returns? Right there's a return. See, these are where the air comes out. That's where the air returns. And it drops a little bit more. So when it comes back, there's no pressure. Okay? So I get 3 volts over 3K, which is 1 milliamp. Does it make sense? Let's pause and look at the homework. We need to cover current sources, but let's look at the homework just to see how unreasonable the homework assignment is. One that's due. All right, so there you got all kinds of practice for your voltages. Here, let's look at this one. Actually, let's do one of these problems and then we'll call it a day. We'll do one of problem 3 and one of problem 4 because this first homework assignment, I really want you to get the formatting down. I don't want any of the homework to be painful, but I'm more concerned with that than anything else. So let's do, which one do you want? A, B, or C in problem 3? C, all right. So let me sketch, and I know you can't see me writing, but I need to be able to see the circuit before I switch over. So let's draw like this, minus plus, and that is 1.5 volts. And then I've got a 1K resistor, 1.5K resistor, and then I've got another voltage, which is 3 volts. And then I've got my ground. And I think this is right. This is called VS, VX. And actually, let's simulate these as well. All right, so what's VS? Plus or minus 1.5? Minus. And what's VX? 3 volts. Before I go any further, anybody not following that? Which way did I sketch the current in that circuit? I don't remember already. Okay, clockwise, yep. So I'm going to put it like this. Does everybody agree that's the same thing? Okay, so what's the current flowing in the circuit? It's this voltage, minus 1.5, minus this voltage, 3, all over 1.5K. Or minus, what's that? Minus 3 milliamps, right? Okay, so let's make sure, because I'm learning, that I draw this out. So this voltage plus minus V and I, so V equals I times R. Questions? You understand this stuff, you have to get your brain wired to look at it. Once it's wired to look at it, it's fine. It may seem easy, but it does take some work and practice to look at things and go, oh, well, that's what's happening and blah, blah, blah. We're going to do it step by step. Okay, any questions on this solution? Yes? I want you to do better than me. But I mean, what can you do? There's not much there. But yeah, I think that's fine, basically. Anytime you do better than me, I'm happy. Question? Okay, remember, what's this voltage right here? Thank you. What's this voltage here? 0. And I've got a battery connected to 0, so I just go to the other side. And here I am. And I'm going to run. And do I go uphill or downhill from there? Uphill. So this is going to be at 3 volts because I'm going minus to plus. Yeah. What's that? Yeah, if you have the pressure on each side, this one's going to be pushing and this one's going to be pulling, and this one pushes, this one pulls, and so we get the bigger current, the 3 milliamps actually flowing like that. But I picked the current like this. But we know the current's actually flowing the opposite direction. That's why the minus sign. One key thing here, notice how if I'm analyzing the circuit, I don't worry about which direction the current is. I pick one and then I solve. And if it ends up being the other direction, oh well, but I don't wait. Which way should I pick the current? It doesn't matter. It's just like when we do Kirchhoff's voltage law. It doesn't matter where you start in the loop. It doesn't matter which direction. Now, if it's in a homework problem or a quiz problem and it says this direction, you say, screw that, I'm going to go this direction. Well, then you lose points, right? Okay, so let's simulate this real quick and then we'll do the last one. Or do you want me to simulate this or not? Actually, let me do the last one. I'm worried we're running out of time, and I'll just simulate the last one. One thing I hated was professors not being able to stop and start on time. So, all right, which one do you want me to do? As if I have to ask. For what? A or B? B. All right, B is a little bit harder, I think. What's 4A as I covered this in class? Tell me the name of that circuit or what I would use to find what the voltage Vx is. Voltage divider. What's Vs in A? 1.5. Oh, the learning's good. All right, so we got our 3K. We got our minus We got our plus and 1.5, and that's called Vs. Current's flowing like that. That's called Vx. And that's 2K. And current's flowing around in the loop like this. And you tell me, did I draw it right? Yes?
When it says very using of this spice, you hold it and just like drop the print it with the root.
Yeah, I'd take and I would snip it, print it out, and put some tape on there, or just print it on a page and write on it. Yeah, for each one. Yeah, I mean, if you want for the first one, like this, you can probably do all of these in one circuit and just take and put one simulation and just have V1, V2, V3, V4 right there, so it's all really concise. You could do the same here, but I think it's probably clearer if you spread them out. Okay, so this one's a little bit challenging, so I'm going to do it quickly for you. And I'm going to say that Vx minus Vs equals 1.5 volts. Tell me why I can say that. Because this voltage is Vx, this voltage is Vs, and a battery is between them. So Vx minus V, I mean, that's the definition of a battery, right? Okay, so now I go back and I say, oh, well, Vs equals minus I times 3K. Because Vs is like this, and the current's flowing from minus to plus, so I put a minus there. Anybody not follow that? Anybody follow that? Do we need our cheat sheet again? Remember, if the current goes from plus to minus, V equals IR. If the current goes from minus to plus, V equals minus I times R. It's really easy once you learn it, but it's hard to learn it. Okay, and then Vx. See, Vs is plus to minus, just like that. Vx is plus to minus, but the current's in the right direction, so it's I times 2K. Yay? Okay, so now I'm going to plug these two in up here, and I'm going to get I times 2K plus I times 3K equals 1.5 volts. Because it's minus Vs, which is minus I times 3K, or I equals 1.5 over 5K, which is 300 microamps. Anybody agree? We ready to sim it, or are there questions? There's a lot of good stuff we're learning today that may seem simple, but you need to make sure you got it. Makes the rest of the semester easier. It's going up the stairs, step by step. Okay, so let's go quickly over here since we got 2 minutes to do the simulation. And we'll go here, and I'll say File, Save As, Example 4. And then I'm going to get the scissors out, and I'm just going to nuke everything. And then I'm going to come over here, I'm going to put a battery in of 1.5. Control R it. And then this is 1.5 volts. Then I'm going to get a resistor out here, which is 3K. And of course, you're going to have this simulation tonight when you do your homework or whenever you do that. And this was 2K. And this is 3K. And I put a ground here. And then tell me, what am I going to do after I've connected all the wires? I'm going to label those nodes so that the grader's happy. Karma, when you're the grader and they don't label the nodes, you won't be happy. So this one is VS. And this one I'll put as VS and then just right click on there and call it VX. And then I'm going to hit save, poke the running man and do an operating point. Okay. And I'm going to get my 3.3 milliamps. Everybody see that? What we calculated? One thing I didn't calculate was the voltage Vs and the voltage Vx. 0.3 milliamps times 2K is 600 millivolts, and you can see right there at the bottom left, and I should have calculated that, and I don't want to go over. And then there's my minus 900 millivolts, 899999999. Does everybody see that? And you can see that now I've done the last problem, and I've done the simulation, and you know how to do it. Have a good day. We'll see you on Wednesday with the quiz.